everyone, welcome to Insights by Arish. Today we are going to perform fashion detection project. So like we have handwritten digit classification using MILS dataset, in similar way we have a dataset that stores the images of various clothing style and we want to detect the image belongs to which particular category. For this project we are going to use this dataset from Kaggle, which is fashion MILS, and as you can see in this particular black and white image, it consists of many types of clothes and accessories as well as shoe wear, and you want to detect which type of fashion it belongs to. So here we have this 10 categories: shirt, trouser, dress, coat, sandals, skirt, sneaker, etc. And these are the labels 0, 1, 2, 3. So while we are predicting, we won't get any particular category as an output. We will get that output in the form of this particular numbers. And if you talk about the MILS handwritten digit classification dataset, in that case you actually have the images stored in the form of arrays, pixels. Here we have that many rows. So considering this dataset, here you have images which are of 28 by 28 grayscale image, and if you say that 28 into 28 is 784. So this particular data set consists of 784 columns. In every column it consists of values for every pixel, and at the starting you have a column named as label, which stores that that particular image belongs to which particular category. And when you download this dataset, you get this folder in which you have a trained dataset and a test dataset. So you are going to use the trained dataset, and then you will validate your model onto this test dataset. So you don't require any 10-test split here because you already have both the datasets provided to you in a individual way. So now that I have downloaded this dataset, it's of 72 MB. I have loaded the dataset into my Google Colab folder, as you can see here, and we'll start building the model now. So first we will import all the necessary libraries that we require. So first we will import the TensorFlow as TF, and then from TensorFlow we will import Keras. So we will import Keras. We will also require Pandas to load the dataset, and NumPy as well. Let's run this. Now that we have loaded all the libraries that we require, we'll load the dataset. So let us say this as train dataset. So train df and read CSV. Into this I will provide the path. As you can see, this is the training set that I have loaded in my Google Colab. I will copy the path from here and I will provide it here. Actually, you don't require this content. You can just supply it with fashion MILS train CSV. Let's run this. And let us try to display the dataset. First 5 rows using the head function. And this is the dataset. As I said, we have 785 columns, basically 784 for the dimensions of image, and one column for the label. As you can see, the first column is label, which holds the categories. If you want, you can also replace this column with its true actual categorical labels, but here we'll keep it as it is, and this all holds the value of pixels. So as you can see, though this dataset won't hold any null values, but still we will check if it consists of any null values. So we will use the isAny function for that, and the sum method to compute the total. You can see there are some columns which consist of null values, and here you cannot perform imputation, because if you perform imputation, then it would basically fill that values with the mean or median of that particular column, and at the end result you won't get the actual image because you have assumed the value on that particular place. So here what we will do, we will use the simplest method, that we will delete that particular rows which holds the null values. So we will use the drop_na method on the train dataset. So train data frame dot drop_na, and we'll also say in place is equal to true to make the changes permanent. So we'll again check for the null values, and I hope we won't get any now. So now we don't have any null values. Let us check the shape now. So initially, actually I didn't load any shape initially. We can do it in, let us check the shape here now. Train data frame dot shape. So now we are having 1886 rows. Actually, I don't know initially how many rows we had. We can check that. We'll again run this things, and here we'll basically check the shape for the trained dataset. So initially it has 1887 rows, and when you perform the drop in method, after that when you check the shape of the data set, it's 1886, which means it just had a single row with all null values. So basically wherever you are spotting this null values, they all belong to the same row. So we haven't lost much of we haven't lost a lot of data here, just a single row. Now that we are done with this, the next thing that we want to do here, we will perform the data normalization here. As you can see in this data set, there are some rows. This particular row, pixel 11, pixel 12 column, actually there are particular columns which holds the value greater than 0, and the values will probably be between 0 to 255. So what we'll do, we will perform the data normalization here to bring all the values between 0 to 1, so that every column will be on the same common scale. So for that, we'll import the min-max scaler from sklearn library, sklearn.preprocessing. We will import min-max scaler, and we'll create an object of min-max scaler class, which is named as scaler. You can name it anything as you want. We don't need to pass any arguments here. And next we will try to fit it. So we'll say that we will use the fit transform method directly. We won't do you can, if you want, you can do both the things separately. You can first fit the model and then you can transform the values, but we'll directly use the fit transform method, which will do everything in one single go. So we'll use scaler dot fit transform, and into that I will pass my training dataset. One thing I can do here, instead of naming it as X, I can say it as train data frame. So this is our train data frame, and now let's run this. So after running this, we'll again try to display the dataset, only the first 5 rows. Now you can see every value is between 0 to 1, which means we have successfully scaled our data. Actually, we don't want to scale our label. We want to keep it as it is. But now that we have scaled it, one thing we can do, we'll again rerun this particular thing. And before the min-max scaler, we will actually divide our data set. So what we'll do here, we can do one thing. I can say the pixels. I can name this data frame as pixels, and I can say train data frame dot drop method I will use, and I will drop the columns, the first column that I don't require, because though I want it in the data set, I don't want to scale it. So I will say label. This is the column, and let me run this. Let me just again display this data frame. Now you can see this is the data frame without the labels column. You can see one column less here, 784 columns in total. So now we will actually perform scaling on this particular data set and not on the label set. Now instead of performing the fit transform method on the train data frame, we will perform it on the pixels. And we'll say the train data frame values, not the labels. So train data frame values, we'll store it in the train data frame values. So let's run this. So I think we should name it as pixels. Okay. Now if you try to display the first 5 values of the pixels data frame, you can see they would be scaled between the values 0 and 1. And so we are done with this. Now the one thing that we require, we want here to do, we are done with the training set. Now let us check the testing set. So we'll say test df, and here we will actually load our test data set, which I have already loaded in the Google Colab. Let's test. I will copy the path, I will paste it here, and we don't require this content. Let's display the first 5 rows of the test data frame as well using the head method. So this is our data set. Again, it consists of pixels and labels. So one thing we can do it actually here, we again need to scale this data frame. So this is the testing set, which already consists of 785 columns, and let us check the number of rows it holds. So it consists of 10,000 rows, and okay, so the training set is consisting of 1,887 rows, and the testing set is consisting of 10,000 rows, which is strange. Actually, it should be vice versa, because the training set would hold more samples than the testing set. So one thing we can do here, what we will do, actually load the testing set on the place of training set, and the training set on the place of testing set. So instead of train, I can say I want to load here the test set. Let me run this. We'll keep the name train df as it is, because we have loaded the test dataset on the behalf of training dataset. So let us check the rows now, and now you can see it holds 10,000 rows, which are appropriate for any training set, because of course it's standard that the train data frame would hold more number of rows as compared to the test dataset. So now we'll perform this. Actually, let me remove the unwanted character here. And now we don't have any null values, but still we'll perform this method, and we'll check if there's any reduction of rows. No. So the training set didn't have any null values. We'll then perform the min max scaling. We'll divide our column of label and the pixels. Now we'll perform the min max scaling here, and let me display again. So now that we are done with this, what we did in when we saw the shape of both the data set, the testing set was holding more number of rows as compared to the training set. So what we did, we loaded the testing set in as our training data set, and we loaded our training set as our testing data set. So on the place of test, it should be train, because we are going to load it. Let me run this as well, and now let me check the shape of test data frame, which would be 1,887. So this is fine. Now the training set hold more number of rows as compared to the testing set. After that, what we need to do, we again need to scale this particular data set as well. So we'll again divide the data set into the label column and the pixels column, and to do so, what we will do, we'll say pixels test, because initially the pixels name is taken by the training set. So we will say pixels test, and into this we'll say test data frame dot drop. The columns that we want to drop here are just a single column label, and let me run this. And then what we'll do, let me just display the first 5 rows of this particular dataset to confirm. Okay, so now it holds no label column. Now we'll perform the min-max scaling. So let us copy the code from here as itself, and instead of pixels, we'll say pixels test, and here as well pixels test. This is what we want. Let's run this, and now we'll try to display the first 5 rows of the pixels test dataset after scaling. As you can see it here, now they are successfully scaled. So we are done with everything, scaling of training set as well as scaling of testing set. The next step that we'll perform is we'll start training our model, because the model is already divided into the training set and the testing set, so we don't require anything much more. To train the model, what we will do here, we will use the keras. We'll say model is equal to keras dot sequential. We are basically using the artificial neural network to train this. So first we'll say keras dot layers dot dense, and here we'll pass how many neurons we want into our input layer. You can see the first hidden layer. So what we can do here, in the first hidden layer, I want, let's say I want 500 neurons. And next I need to input shape, which is so when you check for the training set, you can see the input shape is 1000 into 785. So the input shape, like the number of neurons in the input layer, would be 785. So let's run that. 785. And the activation function that we'll use would be ReLU, the rectified linear unit, which is appropriate for any hidden layer. And this was the first hidden layer. What if I want some more hidden layers here? So let me introduce 2 more hidden layers, and I will say in the second hidden layer I want 300 neurons, and in the last hidden layer I want 100 neurons. And I don't require input shape in the next 2 hidden layers. I just require the activation function, which would be ReLU. Now at the end I will add an output layer, so layers.dense. And as you can see in this data set, in total we have 10 output categories starting from 0 to 9. So the output layer would consist of 10 neurons, and the activation function would be softmax. When you are performing binary classification, in that case your activation function is sigmoid. When you are performing multivariate classification, in that case your activation function is softmax. So now that we are done with softmax, this is the model that we have built. Now we'll compile it. So we'll say model.compile. The optimizer that we will use here would be Adam, and then I will say the loss would be sparse categorical cross entropy. Sparse categorical cross entropy. And now I want to evaluate my model based on accuracy. So the matrix I would provide is accuracy. Now we are done with compilation. The last thing that we'll do, we will say model.fit. Here we need to provide the training set, so X-train and Y-train. The X-train is my pixels dataset. As you can see, the training set is pixels. So the X-train would be pixels and the Y-train would be labels. So the labels are from train data frame. I think this is how it's the train data frame label. So this is my X train is pixel and my Y train is train data, the label column from the train data frame. Let's run this, and it's saying int object is not iterable. Let us check this. Pixels dot shape, and it's 784. So I think it should be 784 here. Now let us try this. So it will take some time to run the epochs. Actually, I haven't provided. We also need to provide the number of epochs we want. It depends upon the number of epochs you provide, how much accuracy you will get at the end of the training of your model. So let me initially you start with the less number of epochs, and depending upon the accuracy that you are achieving, you increase the number of epochs as per your trial and error basis. So for this, I will say the number of epochs I want are 15. Let's say 15. Let's run this. It will take some time. Till the time it's running, let us say loss comma accuracy. We want to also write the code snippet for loss and accuracy. So we'll say model dot evaluate. And as we train the model on this training set, we will evaluate it on our testing set. So the testing set is stored in pixels underscore test. I think that's the name we gave. So pixels underscore test, and we will evaluate it on the test data frame label column. So on the label column from the test data set. Fine. Let's run this. At the end of our 15th epoch, we got the accuracy of 91%, which is quite good on the training set. Let us evaluate our model on the testing set as well to find whether our model is overfitting or underfitting or just accurate. Let's run this, and we'll also print our accuracy. If you want to display it in the format of percentage, we'll provide it with into 100. You can see on the testing set the accuracy is 86% and on the training set the accuracy is 91%. So the difference is just about 4-5%, which is the model is accurate. There's no overfitting or underfitting here. If you want to achieve more accuracy on the testing set, you can do one thing here. You can increase the number of epochs here. You can increase it to some 50 or 60, 70, which would give you the best accuracy here. Now for this particular thing, I would keep it 15 only. Also, if your model is giving you some kind of overfitting condition, like if you are getting very good accuracy on the training set, but when you evaluate your model on the testing set, the accuracy that you are getting is very low, in that case you might try adding some dropout layers here after every hidden layer to reduce the overfitting. Now that we have evaluated our model, we will do some predictions here. To predict, we can say here we will store our values in the pred variable. So you can say model dot predict, and in the predict we can say we want to predict for the pixels test. Let us do this. So we will predict it for the, let's say, for the first instance at the index 1. And you can see you are getting an array of values. This is because you have used softmax activation function in your output layer, which will probably give you these values. If you want to check with the actual values, you need to do something like this. You can say np.argmax. It will provide you with the index at which the value is maximum. So if you go through the array of these values, you can see the maximum value is at the index 9, which means you are probably having the ankle boot. Let us try to do so. We'll say argmax of pred at 1, and you're getting the value 9. We'll also see what is the actual value here. So let us say test df dot, you can say test data frame of label at the location 1, and you can see the value is 9. So actually the value is 9, and our model has also predicted it to be 9, which means the image is of ankle boot. If you want to make some more predictions, you can go ahead. If you want, we can do some more predictions here. Let us say we want to predict the value at the index 100, and the value is probably 8, which means our model has predicted that the image is of a bag. Let's see what the true label has to say. So for true label, we'll just copy this code snippet here, and we want the true label at the location 100, and the actual value is also 8, which means the model has correctly predicted it. As the model is giving 86% accuracy, most of the times it will make correct predictions. In a very rare cases, it will misclassify the things. So we are done with the predictions, and we have started our model by loading the dataset. We have cleansed the model, we have normalized it, we built the model, we compiled it, we fitted it, we also evaluated it about its loss and accuracy, and we also made some predictions. So we are done with the project of fashion detection. I will provide the link of the dataset in the description box. Do check that. That's it for the video. Thanks for watching.